Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. This time we're talking about the results of the most massive stellar explosions that create black holes. They're the supermassive stars that are much larger than, say, 15 or 20 times the mass of the sun. They do weird things. They'll either explode as a type 1 supernova and form a black hole, or just collapse down to a black hole as a collapsar. But we're going to talk about how we know this and the history of it by looking at gamma ray bursts, which are the last vestiges of the formation of a black hole. So let's get going. The first thing is that why do we think about gamma ray bursts at all? Remember, gamma rays are the highest energy form of light, the shortest possible wavelength. They have the highest energies. They're incredibly short wavelengths that we talked about in the spectroscopy and nature of light discussions a while back. But what happened back in the 1960s, during the Cold War, the United States and the Soviet Union realized that all these nuclear bombs they were testing all across the Pacific and in Siberia were causing a huge amount of damage, and it looked like things were going to get out of control. So what people did is they said that the people said, well, we better do something about that. And the president of the time said, let's sign the nuclear test ban treaty with the Soviet Union in 1963. When that was done, it was also trust but verify with the Soviet Union, and researchers at the Los Alamos National Labs built a series of satellites called the Vela satellites. And their goal was to orbit in space and beam down to Earth this constellation of orbits. And their goal was to look for gamma rays, because gamma rays happen when nuclear bombs goes off. So either look for gamma ray detonations in space, which would be part of the nuclear test ban, is a confirmation that nobody's doing any nuclear bombs in space, or on the ground, because they would also form new gamma ray bursts on the ground. So a constellation of Vela satellites was launched. Not long after their launch, on July 2nd, 1967, two of the satellites saw a gamma ray burst, a flash of it that didn't look like a weapon signature. The weapon signature would have radioactive decay of elements that would last like a few seconds. It would be very localized to the surface of the Earth, incredibly bright, and would cause a bunch of different things. But so what they did is they said, well, this is kind of weird, but they ignored it for a while because it didn't look like a nuclear bomb. Then they started seeing more of them, and they found that the Vela satellites, they were wearing out, so they launched some replacements, and some additional satellites, and they were able to clearly demonstrate by using occultation with the Earth that they were not coming from the Earth, they were coming from space. And so since they discovered they were coming from space, they declassified their information and published it in 1973, and thus began gamma ray astronomy. And gamma ray astronomy kind of languished until the launch of the Cosmic Gamma Ray Observatory, the Compton Gamma Ray Observatory, with its onboard instrument BATSE. So this was an incredibly tantalizing mystery, and not knowing where these gamma rays came from, which were the highest energy form of light. No one had ever thought they would happen, but they were coming in these flashes. It's not like there was a constant gamma ray source like the sun or something. Nope, the gamma ray flashes were not coming from the sun, they were not coming from the Earth or the moon, or what seemed like any of the planets. They were coming from the stars. And so somebody figured, well, what caused them? Nobody literally knew, and it was an incredibly hot topic of research. So in 1991, NASA launched the Compton Gamma Ray Observatory as one of the great observatories of NASA's great fleet, which include the Hubble Space Telescope, Spitzer Space Telescope, Chandra X-ray Observatory, and the CGRO. Now, it's one of the more important things for gamma ray bursts was it carried the burst and transient source experiment, the BATSE burst. And so some people say BATSE, but I say BATSE because A is spelled like and. Anyway. But the good thing is it had all these little detectors, one on each corner of the observatory, which you see here being launched from the Atlanta shuttle in 1991. And between 1991 and 2000, it observed over 2,700 gamma ray bursts with its instruments. They found that the gamma ray bursts lasted from about a quarter of a second to up to 30 seconds, and they came in the form of thousands, if not hundreds of thousands, of individual gamma ray photons from specific places in the sky. And there's something interesting about this to me was that I graduated high school in 1996, and in college in Mankato State University, my undergraduate advisor, John Hackala, made his entire career out of looking at the BATSE data. And so in my junior year and my senior year, we worked on some software that would actually determine where these things are coming from in the sky. So it was really interesting to be a college student and then working on this. And then I actually went down to the American Astronomical Society and gave a presentation about the nature of the software on a slightly different way. But what Dr. Hackala did later is that he moved on to Huntsville, Alabama to work on that and discovered eventually that the BATSE gamma ray bursts were isotropic, meaning they came from all locations in the sky. So the colors here indicate the amount of total energy, and the redder they are, the greater the total energy, the greener they are. The middle in blue is the least amount of energy total. You can see that all of these things are evenly distributed across the entire sky. And this is a galactic coordinate where the center of the Milky Way is in the center. Galactic north is at the top, galactic south is at the bottom, and go round and around as we see that. And the dots represent each dot is an individual source location for a gamma ray burst as seen by the BATSE instrument. So if you compare that to an optical image of the Milky Way, we see the Milky Way is confined to a disk with some stars above and below, but the gamma ray bursts clearly are not in the plane of the Milky Way predominantly. They don't even seem to match. They seem like they can go almost straight through the Milky Way center, although there does seem to be a bit of a zone of avoidance smack in the middle, which kind of makes sense given that the center of the Milky Way is directly in the center. So that kind of makes sense. In any event, what we see is that it's not confined to the plane of the Milky Way, and that was a major discovery that became elucidated a couple of years into the BATSE into it, and it didn't take until 2000 for this to be determined. But this was known well into as it progressed. So then the thing was, what the heck are they? What the heck was doing it? Because the BATSE probe could actually give a burst to transit profile. It could give a rough spectrum of it. It knew when they started, when they finished, and how bright they got through time, and they could actually get the rough spectrum of them from different instruments. And so what we find here is that nobody really knew what the heck they were, and this was an open-ended question for a long time. And what were they? White dwarfs, pulsars, new supernova, something in a globular cluster. Maybe quasars were doing it, or Seyfert galaxies, or BLAC objects. We don't even know. Nobody knew. So everybody was saying, we can't tell. But we have to find an optical counterpart to these gamma ray bursts. Somebody's got to find them and see them in order to see what the heck they are. So they said, well, we have to be able to see the gamma ray bursts because they only last a fraction of a second or a few seconds. So we need something that's going to get over to them quickly in the sky so that when they happen, we can see this fading glow of light, because we want to see the gamma ray burst and then see the light from maybe visible. And they needed new satellites and new communication. But the internet really was in its infancy back then, so it was hard to do. So people had phone messages and things like that, and they were contacting that way. Then in 1996, the BeppoSAX X-ray satellite, this was during the operation time of CGRO, was launched by the Italian and Dutch, the Italian Space Agency, and it was an Italian-Dutch satellite launched in 1960. It lasted about 7 years, and it was able to detect the gamma rays and then swing to a different swing to look at them with a lower energy X-ray telescope. So in February of 1997, 1 year after I finished graduate school, not in New Mexico, but in Texas, it caught the first afterglow of gamma ray bursts in X-rays, and then it was followed up with a large ground-based telescope, the Hubble Observatory in the Canary Islands, and it was actually infrared glow from it was seen 20 hours later, and there was a little tiny faint galaxy at that position. Now the hard part was that nobody could get a distance to this thing because the little faint galaxy was really faint, and so nobody could get a distance to it by getting a spectrum. But didn't have to wait long. A few months later, 1997 in May, just 3 months later, another burst occurred, and the follow-up by a ground-based observatory was done in 4 hours, and the host galaxy was found to have a redshift of 0.835. That meant that the galaxy was over 6 billion light years away, and this was the big breakthrough. Those are the two major breakthroughs that said, these things are cosmically distant. So 1998, another burst was confirmed in the same place as a supernova. So a star was seen exploding, and then it's like, wow, now it's not some white dwarf or something. There was a supernova that went off. We know where it is. We know how far it is, and then and other satellites such as HETI 2 were also launched. And HETI 2 satellite was the dominant contributor of looking for gamma ray bursts between 2000 and 2006. However, at the end of that season, the Swift Gamma Ray satellite was launched in 2004. It was renamed the Niels Gehrels Swift satellite earlier this year in 2018, after the person who was the principal investigator who recently passed away. But it was launched in 2004, and that observatory, which is still going, contains 3 telescopes. It looks at gamma rays, it has a gamma ray burst detector, it can swing around and look with X-rays in low resolution, and then it can look in higher resolution with optical light. The best part about it, though, is it allows it to detect a whole bunch of things rather rapidly. When a gamma ray burst is detected, the telescope is a spacecraft, so it slews as fast as it can in a few seconds over and points the X-ray telescope and the UV telescope at that location, pinpointing the location of the source. So it gets a rough general location in the sky, and both these X-ray and UV telescopes are wide field. So the telescope coordinates are then immediately emailed and then circulated now by email, because internet, hello, and it sends it around within about 5 minutes of the telescope doing its slew, and that allows ground-based observatories to follow up. I remember this, and so what's been happening with this particular thing is that as of 2015, the Swift Observatory has seen over 1,000 gamma ray bursts, has communicated to them all the way down to the ground, and its 1,000th observing thing was in 2015. And you can see it also has seen an isotropic distribution, and overlaid on that isotropic distribution of dots is the Milky Way in infrared. So we can see that they're not confined to the plane of the Milky Way, and they're not necessarily associated with the center of the Milky Way. They're cosmically distant. And so gamma ray bursts, we now know, come from, as we saw, came from, at least many of them seem to be coming from distant host galaxies. Then, in 2008, 4 years after Swift, the Fermi Gamma Ray Telescope was launched, and it has a what was a thing called a Large Area Telescope, or LAT, and it can detect very high energy gamma rays and able to make maps of, and make full, very high resolution maps of the sky in gamma rays. And this is fascinating because when it was launched, it created a whole bunch of new mysteries. And there was where does the gamma ray sky have now as a steady background? And it actually found what that was. It's like, wow, what is the background of all of the gamma rays that appear to be in the sky at this high energy level? And the largest known gamma ray burst to date, well, at least in 2008, was known to have, and the gamma ray burst had an energy equivalent of about 9,000 ordinary supernova was seen. And in 2010, the Fermi Gamma Ray Telescope actually showed that most gamma ray cosmic events were probably triggered by supernova remnants or collapsing black holes. In 2013, it detected the highest known photon ever recorded, which is 94 giga-electron volts. That's a pretty high energy gamma ray. If you wish to know how much that is and say, well, it's not very much in terms of watts or joules, but it's the highest known individual photon that's ever been recorded. So it kind of doesn't look like a real telescope. It kind of looks like a box. See that gray box in there? That gray box is the detector, and each of those detectors has these funny subsets of boxes, and inside of each of them is a way of actually detecting the light. And here's how it works: the gamma ray, which is that kind of diamondy thing with a gamma inside, it comes from the top, and it goes into the telescope box. And what it does is there's a whole bunch of foil, and these foils have voltage differences across them. And what it does is that the gamma ray hits this foil. Each of the gray lines is a piece of foil, like a gold foil. I forget exactly the material of the foil, but when it hits the foil, the gamma ray can interact with the particles in the foil. And when it does so, instead of being a gamma ray, it can interact with the material in the foil and create an anti-electron pair. And that's what's happening when the two arrows diverge. That gamma ray has enough energy to create an electron-anti-electron pair, and then that tracks through the detectors, which are the dots. And the detectors say, well, how fast did it go through, and what direction did it go through? And by doing that, you can trace back where the gamma ray came from. And the calorimeter, which is where the electron and the anti-electron go, that deposits the energy of the electron and anti-electron and tells you exactly how much energy the photon had. And so that is how they measured the direction and the energy of a given photon. And so they could detect them all the time. And so the one of them that was detected, they kind of look like this in the sky. And so when they're found, they just look like bright points, and eventually they make a little dot, a little extra set of spots in the sky, and that's what they look like. And this was an extreme gamma ray burst from 2009. But let's take a look again at that one from 2013. And in 2013, in April 27, so gamma ray bursts are named. Every single gamma ray burst has a name. And they're named by 2013, 04, April 27 is the 27th day of April 2013. And A means that that's the first one discovered on that day, because they're sensitive to find more than one per day, and that's happened. And in this time, it found the most energetic gamma ray burst ever detected. And we can see that this is the gamma ray sky image, a full sky image with LAT, that it was taken on that day. And there's a higher resolution version of that that's overlaid to show you just how much energy was on it. I think they rested the LAT on it for almost 2 to 3 hours. It was still emitting gamma rays for hours. And so we can see that this thing is extremely bright, extremely luminous compared to the background radiation. There are background gamma rays that occur. That's what all those blue dots are. Those aren't gamma ray bursts. That's just background gamma ray light from somewhere, from out in the cosmos. But they're not qualified as gamma ray bursts. It's just background gamma ray light. So this is a burst, and we'll see what that really means in a bit. But let's just take a look again at Fermi's sky map. And this is an all-sky map that's taken by the Fermi Space Telescope. And we can see that, yes, there is a significant amount of gamma ray emission that occurs in the Milky Way. But the blue shows there's all these spots of gamma ray emission, this background radiation. We also see a blazar, which is something that we're going to talk about later, and it's looking down the jet of a supermassive black hole that is billions of light years away. We also see 3 prominent pulsars in the Milky Way: the Vela pulsar, the Crab Nebula, and the Geminga pulsar. And the Vela was a supernova remnant that exploded about 11,000 years ago. And the Milky Way center also emits gamma rays as well. So the Fermi Space Telescope has seen numerous things, and most of those faint blue dots that we see in the background are due to light gamma rays that are emitted by material falling into supermassive black holes. So that's where most of the sources come from. So let's see what a gamma ray burst looks like. Here's an example from the Swift Space Telescope. We can see the little graph on the left that shows how bright it gets with time. And what we have is a picture from the ground of a particular location in the sky, and from the ground of the gamma ray burst, and then the UVOT, which is the ultraviolet telescope on board the Gerald Swift Observatory. And there's a tiny, tiny, tiny ultraviolet dot that is there in ultraviolet, but the ground you can barely see it, and the ultraviolet you can see it too. But the gamma ray burst that we see there's a background sort of gamma ray glow, and all of a sudden you get hundreds of thousands or hundreds of gamma rays per second. And so what we're seeing here is that there are over 200 gamma rays emitted inside of fractions of a second. So these things can receive thousands or hundreds of thousands of gamma rays, but at an individual interval of time, you see that we're literally counting individual photons that come into the Swift Space Telescope. And it rises as a burst and fades and then lowers again, then maybe there's a little bit of an after bump later. But that's what a burst profile looks like. Now, all these burst profiles are slightly different. So there's something really energetic extremely energetic that's creating these gamma ray bursts, and we can see that this is an energy range of moderate X-rays, or moderate and weak gamma rays. from this particular sensitive region in the gamma ray burst of the Swift Space Telescope. That's what that 15 to 350 kilo electron volts means in the upper right of the profile. And notice the length of the burst starts at 0 and goes no longer than a second, and most of the burst is done by half a second. So it kind of starts at a quarter of a second. So you see that there's like a background, you got background and then foreground, and then it triggers the alert, and then it records the alert. And the trigger happens at about 0.2 seconds in. And when that trigger occurs, it sees that, it rises to a peak at 0.4 seconds after time, and then is done by 0.06 seconds. And maybe some after bumping of about a second. But the vast majority of it is done in about less than a half a second. So how do you find these things? That's what the Swift telescope does. It slews quickly over to look at the ultraviolet, UV, and then X-rays as well. All right. This is typical of the profile, because when we look at the BATSE instruments that my advisor John Hackala looks at, here are 3 from the early launch platform of the BATSE Observatory, and I give you the where you can actually download these too, and we'll go look at those in just a second. And we can see some of them are quite energetic, and none of the profiles look identical. Sometimes they're long, like the middle one is many tens of seconds long, or they can be incredibly short, a fraction of a second, like on the right-hand side. Or they can begin and go to a really fast peak and then drain away, just like we see in the first one. Look, there is almost no periodicity to these things. However, there is some bumpiness, and that is a subject of active research, is finding patterns inside of these things. And that's what my advisor, John Hackala, has just found, has a recent paper that discusses that, and we'll talk about that. So the hunt has been on since the 90s to discover patterns in the behavior of these gamma ray bursts. All right, so here's more of the gamma ray bursts from John Hackala. Well, he wasn't one of the BATSE members, but he's been active in doing data research on the extensive data set of BATSE. And what we see is that, look at all these different kinds of data sets, and each of the y-axes on these things is thousands of photons counted per second. So these are incredibly energetic things. And it's like, what is the real profile? So it's just very puzzling exactly what's making these things. And if you then group, well, how long do they last? If you take the entire BATSE catalog and say, how long do they last? You find that there's 2 groups. There's a short period group with that peak in the short periods, it's at less than a second. And then there's long period ones that are between, say, 10 seconds and up to a minute or so. So there's 2 basic peaks. That means there's 2 basic types. Gamma ray bursts are either short, less than a second, and fractions of a second, or they're long, 10 seconds up to 30 seconds, maybe up to 100 seconds. So there must be 2 different processes, 2 dominant processes that create gamma ray bursts. So perhaps there's a supernova that does it. All right, so the Hubble Space Telescope when the Swift Observatory launched and saw one, we see the Swift UVOT image there. It's like, oh, there's something, and that's in 2006. And Hubble afterglows, looking for this particular one, found it, and you can actually go and hunt following up for fainter and much more distant objects. And long gamma ray bursts tend to have supernova counterparts, and that's what we see with this UV image. So they have some sort of glowing afterglow, like a supernova remnant. And that seems to be pretty common, that the longer ones have them. But if we then we go back to that, one of the most massive ones ever known was Swift detected an incredible gamma ray burst, and in March 19 of 2008. And there was the left-hand side image is the UV image, and the right-hand side is an optical image as well. So what we see is that the images actually the right-hand side is the UVOT image, but what we see is that it found a gamma ray burst and swung over and saw it, and it was one of the farthest objects that could ever be seen without a telescope. This lasted only for about 60 seconds or 30 seconds or so. And when it got to its brightest, this object, it got so bright that if you were looking in that direction with your eye, and we were in a dark sky with no clouds, you could have seen a bright point of light just appear, not bright, very dim, just on the boundary of visibility. If you were up in a dark location like the Grand Canyon or Cherry Springs State Park, or a lot of any other really true dark locations, you would have seen a new star appear and disappear 30 seconds later, and you might have thought it's a meteor or something. Well, a very dim meteor. And the magnitude, it stayed bright as magnitude 9 for about 60 seconds. And later follow-ups on this thing showed it had a redshift of 0.937. That meant its distance was 7.5 billion light years. And anything that can be seen naked eye from that far away means it was about 2.5 million times brighter than a supernova. This is just wildly bright. It's like 2.5 million times the brightness of a core collapse supernova. We've already known that these are the brightest, that outshines a host galaxy. So we now have something that outshines, we now know stars that explode, supernovae, that can outshine 100 billion stars, and this is 2.5 million times brighter than that. So what we're doing is we're looking down the top of a gamma ray burst jet, because it can't be isotropic. That'd be too big an energy at budget. So something's got to be doing that, that's collimating it and focusing it, because that's just too bright if it's isotropic. So let's actually see what that brightness looked like. And this actually was seen with a camera, actually, and it was observed at 2 o'clock in the morning Eastern time. So if you were in Maine, you could have seen this, or if you were even down in southern New Jersey at Southern Jersey Astronomy Club in Bella Plaine State Forest, you could have seen this. So, but there's the movie that I'm showing is from a Polish group called Pie of the Sky that looks for little transient afterglows. And so what they do is they have all sky cameras, and they detected it. They got it. And later that evening, the Hubble, and it was because it was swift, the alert went out, and in fact the Hubble Eberly telescope way out in West Texas actually was pointed at it and was able to take a redshift of that location prior to it going out. And this was the brightest object ever seen that could be seen naked eye, which is astonishing. All right, so when they get bright for a while, and sometimes we see their visible light sometimes. Well, the visible light can actually be something there, so it can happen, but it's not necessarily all in gamma rays. So gamma ray burst also has an optical counterpart that has been seen, and so there's two bits of it. The first bit is you get the gamma ray burst, and then you might get something, a glow of some kind, maybe what we call a hypernova glow, that happens later. And there's a bump in a bright, so there's the initial burst, and then it dims and dims, and it gets bright again, and then fades away. So there's two counterparts to some of these when we look at them through time. And in visible light, there it is. There's one that was seen in visible light with very, very faint. This is not naked eye now. And then later on, that one's fading away, and we can see that they start really bright. The gamma ray burst is seen by Swift, tells everybody, and people try to follow up and lots and lots and lots of follow-ups. Well, that's really interesting. And as people try to discover what the heck is going on, my advisor just had something very interesting that got published in August of this year, 2018. And what he was actually doing is looking at the nature of the BATSE profiles. And so he took a number of these profiles, meaning how they get bright with time. And he noticed there's kind of a triple peak to them. Frequently, there are 3 peaks that can be teased out of the data after you clean it up a bit. And so they do some smoothing of the data and find 3 peaks inside of the data. And then if you normalize those 3 peaks, you find on the right-hand image, you see the blue background, which is the actual gamma ray profile. The white overlay is the smoothing profile that they apply. And then if you then remove that and make an average out of it, a time average of it, you get the left-hand profile, which is in yellow. And there we have a bump in the beginning, a bump in the middle, and a bump at the end, which is kind of what they called it time reversed, which is weird. It's kind of like saying, no, time is not being reversed, but however, the profile looks the same going forwards in time as it does going backwards in time. So according to the left-hand curve. The actual profile, as you can see, gets brighter and then goes dimmer. But it's very strange to think that it has this kind of wave packety sort of appearance that looks the same forwards as backwards. It's probably due to the same interaction happening on one side of the explosion as it is on the other. So we see one side of the explosion, then we see the other side. And so the triple peak thing says, oh, it's the whatever's happening on one side is happening on the other, and it's nearly symmetric. So we get this three-dimensional thing. But anyway, I just kind of scanned his article. I would invite you to go take a look at it. He published it recently in AppJ, and he's got tons of fun stuff. If you just Google time-reversed gamma ray burst, you'll see it. It's all over all sorts of sites. It's a lot of fun. And that's my friend and advisor who is still going strong with this wonderful data from BATSE and Compton Gamma Ray Observatory. All right, so let's look more closely at some other gamma ray bursts. The distance measurements over time have yielded that these things can be really far away, up to 2 billion parsecs, 2 gigaparsecs, billions of light years away. So we're actually looking at things that happened in general a long time ago, not things that seem to be happening now, because most of the gamma ray bursts are distant, not local. So it seems to be more of an ago thing than a current thing. So therefore the light is only reaching us now. And if it's 2 billion parsecs away, and it's been redshifted down to gamma ray bursts, these things are insanely energetic with what they pump out of light. All right, so the gamma ray bursts have host galaxies, which we see in the Hubble image on the right, and the Swift sort of CGR image on the left. And the Hubble Space Telescope has done numerous follow-ups and found that they're almost always in star-forming active galaxies that are extremely faint, from 2 billion to 10 billion light years away, and they're always in these tiny, misshapen, ancient galaxies that are in their formation stages. The only real exception to this is in the middle one. The green crosshairs show you where the burst has occurred, and that's also the Hubble Space Telescope went and did a follow-up too. The only different one is the one that's in the middle top, which is actually a little tiny spiral, which is relatively nearby. But all the bright dots are nothing to do with that. Those are foreground stars from the Small Magellanic Cloud. So we can see these gamma ray bursts are associated with star-forming regions, with vigorous star-forming regions, with vigorous areas where things are happening in the early universe. So what we have is a picture of a model of where these things come from. And it's called a hypernova. A hypernova is something where you have a supermassive black hole forming, but it's forming in a gaseous, dusty medium. And then there's a jet that punctures through it and disrupts this medium. So as it forms, so what we have is, so think of this as a curl that goes from the back all the way to the right, then to the black hole at the center. We start with a pretty much uniform, very low metallicity star, mostly hydrogen and helium, almost no other metals. That's very massive, maybe 40 times the mass of the Sun. It evolves extraordinarily rapidly over a course of a few million years and builds up to an iron core and then does core collapse. Now this is similar to all the other the supernova that we talked about in previous lectures. However, the core collapse, because it's a 40 solar mass star, is catastrophic and even faster than than we found when we looked at supernovae of like stars that are between 8 and 15 times the mass of the Sun. What we find is that in the center of the star, a black hole is formed immediately as the star is collapsing. And inside the core of the star, this black hole, remember the black hole is only a couple miles in diameter, which is very tiny compared to the entire size of the star, which might be it might be like 100 times or maybe 400 times the diameter of the Earth, or more like 600 times the diameter of the Earth for a 40 solar mass star. So that's an incredibly large object compared to this tiny black hole. So down in the core of the star, as material is raining on top of it, an accretion disk forms inside the black hole. Around the black hole, as material tries to fall into it, and the black hole material doesn't quite hit the center. It misses the black hole, forms a massive accretion disk with a huge magnetic field. The magnetic field makes a jet, and the jet punctures its way out of the star and rips the star apart. So this is kind of the gamma ray burst model for forming a black hole. The supermassive star collapses inside the star. While it's collapsing inside that quarter second, less than a tenth of a second to form the black hole, form the accretion disk, and then the jet appears. The jet comes out of the center of it, punctures through the entire star, and when it does so, low energy gamma rays are created by the jet of material puncturing through and shock heating it up to millions and billions of degrees, which then emits gamma rays. These shells then go outward and outward. These are ruptured shells, and as the shells collide with other shells of gas, I mean, they're like, think of it as, instead of a shell, like these, not just shells, but waves of gas that are coming out. And these things, as the shock waves hit, they heat the other gas, and that's what forms more of the gamma rays that we see inside of the gamma ray burst. And that's what we call the prompt emission, which is the sharp spike upwards in the early part of the gamma ray burst. And then the afterglow, which is now the hypernova part of it, is that these shells then crash into the interstellar medium around that, and that creates visible light, radio light, X-ray light, and more high-energy gamma rays. So there's a very, very, very fast jet that goes and smashes into it, which creates huge amounts of gamma rays, but the waves from the jet keep going and eventually collide with the ambient medium around it and create the afterglow that we call a hypernova. So let's take a look at what that kind of looks like. It's a really interesting thing. Notice we got this stellar disk, this dusty material around, and inside the dusty area, there's the star that's in the middle. It's already gone supernova down in the core, and now the black hole has punctured through, and this jet is moving almost the speed of light. So it went out in a few seconds. Now it's going, we're looking at something that's moving almost the speed of light, puncturing through, and as the jet collides with the material directly surrounding the star that occurred as the star died, it heats the medium, causing shocks, and that shock emits huge amounts of gamma rays. And those gamma rays then, if we are looking right down the jet of these hypernova, we see a gamma ray burst. And that's where the gamma ray burst that was super bright, seen in April 27 of 2013, occurred. Now the shell that's around it is really important too. But there's the supermassive star. And again, it's all because of a black hole that has formed deep in the center, that's formed in a fraction of a second with material going around an accretion disk, and then that accretion disk creates a jet, and that jet punctures its way out of a 40 solar mass star and shreds the entire star apart as it does so. So that's the source of that massive gamma ray burst that was seen in April of 2013, and that's where it comes from. And what about these things that's interesting is that there could be things in the Milky Way that might become them, and they're called the Wolf-Rayet stars. And Wolf-Rayet stars are supermassive stars, more than 15 or 20 or even 40 times the mass of the Sun, and they have these huge, huge, huge stellar cocoons around them. And this image is from the Hubble Space Telescope of the nebula is called M167, which is the nebula surrounding the Wolf-Rayet star, WR124. So the stars at the center, the nebulas at the outside, and Wolf-Rayet stars are incredibly rare because they're incredibly large. And the stars themselves, when seen in aggregate, their spectra have ionized helium and nitrogen and carbon, and that's from the nebula as it ionizes that stuff. And then the spectra of the star itself shows very high surface enhancement of heavy elements and almost no hydrogen because that's going out into the nebula. And then there's incredible stellar winds, but the surface temperatures can be up to 200,000 Kelvin, which is hotter than which is about the surface temperature of a neutron star, and it's hotter than pretty much every other star. So these stars are going to blow up, and they'll blow up really soon. So at some point, so they only live millions of years before they explode. And then we can see that there's a few that are naked eye, such as Gamma Velorum, and then the constellation Vela. And then there's Theta Musca, which is both of these are southern constellations, and by Gamma and Theta, that means these are pretty bright stars in those constellations. Gamma meaning alpha, beta, gamma. The third brightest star in the constellation Velorum is the Wolf-Rayet star. The most massive star is in the star-forming region 30 Doradus, is a Wolf-Rayet star as well. All right, now, did this happen nearby? Well, maybe. It's possible that Casanova A, that the Cas A, which is a supernova remnant that we talked about in supernova remnants way back in a previous lecture, could it be a gamma ray burst supernova? Remember, Cas A doesn't really have much of an optical counterpart, so maybe when it exploded, there was a hypernova, not a supernova. And we can see that there's definitely a high velocity jet that's still occurring, that's still shredding this supernova remnant. And the right-hand side is the Hubble optical image, and the Chandra X-ray Observatory shows evidence for a jet as well. So maybe this very recent supernova was a gamma ray burst supernova. So they might have happened in our Milky Way. All right, so that leads us to the two, we're going to now go a little crazy, but remember there were two different kinds. There were two different burst sources, and these types of things create long burst supernovae, long burst gamma ray bursts. So where's the other one come from? So the bottom one are the long bursts, where you have some sort of collapsed star. This inside, the black hole forms deep inside the supermassive star. Sometimes the collapsing star is called a collapsar. And a supernova forms, the black hole forms deep in the core, and the accretion disk forms around the black hole inside the star, and that re-shreds the entire material and then pushes everything apart, recreating a supernova. Now we call it a hypernova. And that's what we get. And that relativistic outflow that we saw in the movie, relativistic means it's getting really close to the speed of light, and then you get supernova type remnants that occur from that long burst. However, there's another way we can create them. If we allow two neutron stars to collide, they too can do that. And a neutron star collision would last fractions of a second. So if you take two super dense neutron stars and collide them together, it makes a very, very, very high temperature disk that then explodes and creates a gamma ray burst. And here's kind of what that might look like if we have two neutron stars that are colliding together. This whole process would take less than a few milliseconds because their separation would be on the order of a few miles, and then they're also a few miles apart. And so what this is would be radically slowed down to exactly what it would be. And when they finally do collide, after they do, they would create the gamma ray burst that we see, and there's the burst going outward from that particular star. And then they could be modeled with a supercomputer. And this is from the NASA visualization by Compton Gamma Ray et al. So you can go check this out, and I'll provide a link later. Is that the jets may actually be provided because neutron stars have incredibly strong magnetic fields, and the magnetic fields were attached. This is a computer simulation showing these two neutron stars with their embedded magnetic fields, and for a very brief time during the coalescence, a black hole forms in the center. But the magnetic field stays entrained inside of the nebula that surrounds it, that lasts literally only a quarter, like 26 milliseconds, or less than a quarter of a tenth of a second. So it's a quarter of a tenth of a second. Faster than you can, it's about 3 hundredths of a second, which is really fast. That's faster than you blink. So this all happens faster than you can blink, which is astonishingly fast. And so what's amazing about this, what about that short gamma ray bursts that can create neutron star collisions, is that we have actual evidence for these neutron star collisions. And one of them was actually a visual thing that occurred on August 17th of 2017. An incredibly important discovery happened on that day, and we see the afterglow of this particular supernova that occurred by the collision of two neutron stars with the SWOPE supernova survey. And on the night of discovery, on August 17th, there was a bright supernova that occurred there, and 4 days later it was still glowing with the hypernova that surrounded it. Something happened there, something wonderful. And that's what we'll talk about next time. See you soon.